Dear students, welcome back to our NPTEL course on analog electronic circuits. Myself Dr. Pradeep Mandal from ENEC department of IIT Kharagpur. So, today's topic of our discussion, it is common emitter amplifier. So, this is a basic amplifier, and many of the concepts need to be getting clear in this amplifier. Some of the prerequisites we already have covered, which are necessary to understand and appreciate the operation of the common emitter amplifier. So, according to our overall plan, let us see how we are into the overall plan. So, in the overall flow, we are in week 3, and in the previous day we have discussed about the amplifier models, voltage, current amplifier, transconductance, transimpedance, and so and so. And then we also have a plan to cover cascading multiple amplifiers, but we will be covering after we consider some of the practical circuits like common emitter amplifier and common source amplifier. So, today's main discussion here, it is the common emitter amplifier and its working principle, biasing scheme, then analysis, maybe some part in case if time permits we can cover some design also today or maybe next day. But I must say that so far whatever the topics we have covered, namely the device model and then methodology of analyzing nonlinear circuit, and then the notion of small signal and large signal model of the BJT and maybe MOS. Those concepts it will be frequently used. In fact, while we have explained about this small signal model of BJT or MOS, we have discussed some extent about the operating principle of the CE amplifier. So, we may not be going detail of, or rather we will not be repeating whatever we have discussed in the circuit operation. Rather our primary focus it will be on biasing and then the corresponding analysis. So, what are the concepts we are going to cover today? It is we will start with the operating principle of CE amplifier, but again as I said that we will not be going very deep into that. And then main thing is that the biasing of CE amplifier. In this course primarily we will be covering two types of biasing of BJT amplifier. One is fixed bias, and then subsequently we will see that what may be a better option. And then in the fixed bias CE amplifier we will see that how we find the operating point, and then how do we get the small signal model and small signal analysis. And then we will be covering the what are the issues are there, particularly very common issue, it is called DC operating point is very sensitive to beta of transistor. So, as a result, in case if you are replacing a transistor by another one having different beta, then its operating point completely gets shifted elsewhere, or in the beta may not be changing due to replacing the device, it may be due to temperature effect, and due to maybe higher temperature beta will increase, and then that directly affects the operating point of the common emitter amplifier. So, that issue we will be discussing, and then we will be giving a pointer what may be a better option or the solution of that problem. Okay. So, yeah. So, what we have the CE amplifier again will be just touching the basic operation, but before that I must say that whenever we call the common emitter amplifier, the input it is fed at the base of the BJT, and then output it is observed at the collector node. So, you can see that the input we are feeding here, and then output we are observing at the collector node. And whenever you are considering signal at the input and output terminals, normally the signals we are considering in the form of voltage. It is possible to consider input signal in the form of current as well. So, likewise output also can be considered as current. This same CE amplifier, it may be considered as current amplifier or transconductance amplifier or transimpedance amplifier, depending on our specific interest, but predominantly, unless otherwise it is stated, this CE amplifier it is considered as voltage amplifier. So, what does it mean is that, as I said, that both input and output signals are voltage. So, whatever the analysis we will be doing now is basically from considering that the signal will be feeding in the form of voltage, namely the signal source resistance, Thevenin equivalent resistance, we want it should be as small as possible. And while we will be observing the output, we may not be loading the circuit by any load at the output, namely parallel resistance at the output. So, that it need to be taken care. And now, let us see how we proceed. At the input, you can see that while you are feeding the signal, it is also accompanying a DC voltage. And while you are observing the output, this output may be having a DC part as well as the AC part. So, probably the AC part we can extract, we can block the DC by a capacitor at the output, but typically getting a signal source having a appropriate or having a meaningful DC voltage is most of the time it is not possible and feasible. So, whatever the input port we are considering here, namely the small signal source in series with DC voltage, and that DC voltage should be appropriate for the BJT, may not be you should not be expecting. So, it is of course, it is having some practical circuit. So, we will be we will be discussing about the practical circuit, and also the voltage amplifier parameters, namely voltage gain and input resistance. Those parameters values are very strong function of the bias condition or the operating point of the transistor. So, designing one amplifier, it is very important to consider the biasing concepts, how we get the operating point. So, let us go little detail of that. So, in the next slide we will be discussing that, but here as I say that since you are looking for the circuit as a voltage amplifier, typically this is the small signal model of the voltage amplifier, right. And as we can see that this is the boundary of the amplifier. It consists of open output voltage gain AV, then also it is having output resistance RO, and then the input resistance of the amplifier, which we have discussed about the these three parameters and significance of these three parameters in voltage amplifier model. And these three parameters, of course, they are very strong function of the operating point, right. So, this is one important point, that while we like to get a voltage amplifier having a good steady gain, we need to keep the DC operating point appropriate. In addition to that, since we are feeding the signal here, signal it is voltage. So, at the input the signal it will be in voltage form, which may be having Thevenin equivalent resistance called Rs. So, likewise at the output, while we will be observing the corresponding output, we need to consider only the signal part, and when you consider signal, it is expected that in case if we are connecting any load, this load should not be directly affecting the operating point of the circuit. Otherwise, this load may change the operating point, and then indirectly they may change the small signal parameter. Yeah, so we need to be careful while we are fixing the operating point of the circuit, or the biasing of the circuit need to be properly taken care. Okay, so what we are considering now, practical circuit, biasing circuit. So, what we have, it is the requirement wise, as I said that at the input we do have a signal which is riding over a DC voltage. In this case, we are calling this is VBE. So, likewise at the output we do have a DC voltage. So, we need to remove those things. So, just now what I was telling that to have meaningful operation of the amplifier, we need to keep this transistor in active region of operation, right. So, active region of operation. So, for that we require a meaningful DC voltage that is supposed to bias the base to emitter junction in forward biased condition, and likewise at the output it should be having sufficient DC voltage. So, that while at the output we do have a signal, and the instantaneous output voltage should be sufficiently high, even in this critical case when the signal it is going to the minima. Even then this junction base to collector junction should remain reverse bias condition. Otherwise, there will be huge distortion at the output. So, it is very important that the operating point should remain constant, so that the gain should be remaining constant. And the second thing is that the DC voltage here should be appropriate, so that the base emitter junction is getting forward bias, and whatever the bias we do have here, for that the DC current, which is DC current collector current flowing through the transistor, which is incidentally flowing through this RC, then whatever the voltage we are getting here, namely V capital C, that should be, so this is the V capital CE, that voltage should be sufficiently high, so that while the signal it is riding over that, the instantaneous voltage, even in this critical condition, the transistor remains in active region of operation. So, on the what may be the practical circuit, let us look into that. So, as I said that biasing is very important. Yeah, so let us look into the input port. So, what we are talking about, the whatever the equivalent circuit we can see here, and then after that we will see the output port circuit here. So, the input port, if I consider, here you can see at the input port we do have this RB, which is connected to base terminal of the transistor, and base to emitter terminal we do have a diode, forward bias diode. So, equivalently I can say that we do have RB in series with a diode. Of course, this diode it will be slightly different kind of normal diode, namely this junction, though it is forward biased, but most of the collector currents are coming from the emitter junction. So, as a result the level of current flow here it will be less. However, if I consider the current and voltage characteristic of this diode, obviously it will be having the exponential relationship. So, for this analysis definitely we can consider this is similar to a normal diode. Now, this diode can be replaced by its equivalent circuit, which is shown here, which is having a DC voltage in series with on resistance of the diode. The on resistance of the diode here we are representing by R pi. It is primarily coming from the pi model of the BJT, but for the time being you can consider it is on resistance of a diode, and this resistance it is very similar. Now, once we have say supply voltage and this circuit connected, the DC voltage coming here, it is I can say that VBE. So, we can say this DC voltage it is VBE on plus R pi multiplied by this current, whatever the current we do have here, called say IB, I capital B. And this IB on the other hand, it can be obtained by considering this loop. So, that is VCC minus VBE on divided by RB plus R pi. Practically this resistance it is very high, in the range of few hundreds of kilo ohms to maybe mega ohm, and R pi on the other hand it is very small, its value it will be in the range of few kilo ohms only. So, since this is hundreds of kilo ohms and this is kilo ohms, so you may ignore this part, and then from that you can consider the IB, and from that you can find what will be the DC voltage coming, and that DC voltage it is this DC voltage. Note that this base current as well as this R pi typically it is very small. So, this part it may be very small compared to VB on. So, we can say that this DC voltage it is very close to VB1, but slightly higher. So, once we have the DC voltage obtained there, next thing is that the capacitor it is helping for the signal to feed in. So, we do have this coupling capacitor, signal coupling capacitor, which is coming from in the original circuit there, and so this signal frequency we assume that it is sufficiently high compared to the cutoff frequency defined by this C and the equivalent resistance coming there, or you may say that the value of this capacitor it is sufficiently large, so that the signal it is directly coming to this point. So, at this point if you observe the voltage, instantaneous voltage, it is having a DC, on top of that it is having the small signal. So, it is equivalently it is making a small signal riding over the DC voltage. So, it is riding over the DC voltage. So, earlier we are having this simple stimulus at the base, but of course, it is an ideal model. Practically this is how it is obtained, by combination of this RB and C, we are getting a voltage here which is having a meaningful DC, and on top of that we are successfully feeding the small signal. Okay. So, we will be seeing that what may be the equivalent circuit of this one later, where small signal equivalent circuit, where we may short this capacitor, and then this DC voltage you can consider it is AC ground, and then this DC voltage you can drop. So, for AC signal will be practically will be having this RB and this R pi, and then this signal it is also coming. Since we are not considering any Thevenin equivalent resistance here, this resistance it is 0. So, as a result this voltage it will be for AC signal it will be directly VC. So, just now what I said is that for this is the total signal, total circuit, and for small signal on the other hand at the base we do have only the Vs coming there, and then this is the base node, and at the base node we will be having this corresponding R pi, which is connected to ground. And then of course, we do have the RB also there, but since this RB, as I said, it is very high, we may ignore. And then we do have the DC voltage here, which is of course the AC ground. And so that is what the voltage it is coming to the base terminal. In case if we have a, so the signal here it will be across this R pi, it will be same as Vs, but in case if I consider a practical source resistance, say Rs, then of course the voltage here it will be slightly different. So in that case these two resistances we can map into equivalent input resistance together, and these two together practically it is coming R pi only, and then this R pi, so this R pi it is and then Rs, they will define what is the voltage coming here from the signal source. So to further conclude what we will be having at the base, we do have for small signal at the base we will be having the Vs having a source resistance Rs, and then the base to ground node resistance. This resistance it is parallel connection of Rb and R pi, but we can say this is R pi. Okay. So this model will be using whenever we will be talking about the small signal analysis. So at the base, that is the equivalent circuit we do have at this point. Now let us look into the output port of the circuit, and let me draw the corresponding the equivalent circuit. To start with, we will be going for the large signal first, and when you consider large signal, this IB, whatever the IB, it will be flowing here. After multiplying with beta f, we do have IC here. So this IC, it is coming from this IB after multiplying with beta f. So we have to be, we are assuming that this circuit, once it is decided, next thing is that, so which means that the IC it is also getting decided, and then we can see what is the corresponding voltage coming here. So let us look into the output port in the next slide. Yeah, so at the output port, what we are expecting that voltage here it will be like this. It is shown here. It is having a DC voltage called say V capital CE. Incidentally, this is CE, or you may call this is V capital out. So this level we can say capital V capital out. On top of that, we do have the small signal. So we do have the small signal here. So now this small signal, of course, we can extract by, as I said, by placing this capacitor. So we will see that part, but initially the DC part, what we have it is we do have RC connected to VCC, and then we do have the collector to emitter voltage. So we do have the collector to emitter current IC. So this IC it may be having both DC part. So this IC may be having two currents. One is DC part I capital C, and then also the small signal part. small I C, right. And then this I C, capital I C, as I said that it is beta times I B, whereas the small signal part here, whatever the small signal we are seeing here, this is also beta multiplied by I B. So, this beta it is slightly different from beta F. It is called large signal beta in forward direction. This is called small signal current gain beta, but practically we may consider both are equivalent, but you need to be careful there, they are not exactly same. And on the other hand, the small signal current here, it is this beta multiplied by I B, and this I B, it is essentially it is coming from the V S divided by R pi. Okay. So, we will see this pretty soon, but just to say that the current flow here, it is having DC component and the small signal component. Then we do have, if I consider the voltage at this point. So, voltage at this point, we do have DC part, it is generated by this DC current RC and VCC. So, we do have this V out, just now what we said is V out, which is VCC minus RC multiplied by I capital C, which is of course beta into I capital B. In addition to that, we also have small signal part. So, we may call small V out. So, what is that? It is for that small signal, this is ground, and so we can say this is ground and the IC current is flowing here. So, we may say that this is minus RC multiplied by IC, and this IC, as I said, that this is beta times IB, and on the other hand, and this part it is beta F times IB. Okay. So, now we do have both the DC part and the AC part together, that gives us this signal. So, instantaneous signal. Now, by placing the capacitor here, by placing this capacitor here, we are removing this DC part, and at the output what we see, it is only this part. So, if you are observing the signal here, what we will see that it is a small signal with respect to ground. So, with respect to ground, and we call this is small v small out, right. Now, if I combine this information together, we can get the small signal equivalent circuit. So, in the next slide, we can look into the corresponding small signal side equivalent circuit, but let me take a break and then we will be discussing in detail of this one.